Ladies and gentlemen, welcome to our video course, The Power of Language. This course is part of the educational series of the Science and Life project. Here is an outline of the contents of our course. The course is divided into 9 units as follows. A. The importance of language. B. The symbolic identity of the human being. C. Basics of set theory and equivalence relations. D. The general structure of a logical language. E. The general problem of definability. F. Fuzzy sets, fuzzy logic, and rough sets. G. Dynamical systems and chaotic systems. H. Main theories of meaning in natural languages. And I. The ontological power of language. Creation, change, and destruction of realities by language. We begin now with the first unit called The Importance of Language. The main aim of this is to make clear why it is so important to study and analyze the general structure of language as a fundamental knowledge to better understand all human thought, actions, and relations, going from all the sciences to everyday life. To this end, we will define first the concept of a sign. A sign is composed of two entities, two objects in its broadest sense. They can be whatever you like, physical or mental. A sign is defined as an ordered pair consisting of these two objects. The first one will be called the signifier, and the second one will be called the signified. Very often, the word symbol is used for the first object too, and the word meaning for the second. So a sign consists of a symbol object and a meaning object. Take any two objects of whatever kind you like. Say objects A and B. They don't have to have any similarities or anything in common. The fact that we want object A to represent, to stand for object B, means simply that we are mentally making an association between the two. We are assigning object B to object A as its meaning. We have drawn an arrow from A to B to express that object A signifies, represents, or symbolizes object B. That is, object B is the meaning assigned to object A. We can freely create whatever associations we want between objects, and so a sign can be completely arbitrary. Following pairs are examples of signs. 1. A name as a phonetic or written object, and the bearer of that name, the physical person, like Daniel and the person named by this name. 2. A second expression or utterance like party and the corresponding situation, event, or action it refers to. Of course, mental entities associated to that signifier can also be taken as its meaning. As said at the beginning, signifier objects or meaning objects can be physical or mental. 3. A ball can be the signifier of a galaxy if I define it to be that. The galaxy would be the meaning or meaning object of the ball in that case. We would say that the ball represents the galaxy. 4. The visual perception of a flower, that is the image our brain forms from outer world signals or sense stimuli, can be taken as a signifier or symbol of the flower per se, that is, as a being outside our mind. A first and primary definition of a language could be simply as a set of signs. A language is a set of signs, each of which consists of an ordered pair of a signifier object and its signified object or meaning object. The set of the signifier objects, together with the rules that define which signifiers are allowed, is usually called the syntax of the language. Every allowed signifier is called a formula of the language. The set of the meaning objects of the language, together with the rules how meanings are built, is normally called the semantics of the language. So you see that H2O, for example, is a formula in the language of chemistry. That is, an allowed signifier in that language, and its signified object or meaning object could be a standard molecule of water. In the same vein, a physical rose can be a formula signifying love feelings, for example. The rose would be the signifier object, and the mental love feeling processes would be the meaning object. Examples of languages are the so-called natural languages like English, German, French, Spanish, Chinese, and so on. The formulae there are the written expressions or utterances, and the meanings would be the things, phenomena, actions, situations, etc. they refer to. In these so-called body languages, the formulae will be gestures, face expressions, body positions, etc. In mathematics, as the language of physics, the formulae will be the allowed mathematical expressions, and their meanings would be relations and objects in the world of physical phenomena and processes. In the language of art, the formulas would be the artworks themselves, and the meanings would be whatever mental contents are caused by them in the observer. As each observer will associate different meanings with the same formula, that is artworks, one could talk in this case of private languages, that is, languages the meanings of which are different for each observer, even if the formulae are the same. Now, why is the concept and understanding of language so all-important? Because literally everything else, every kind of knowledge, already presupposes a language in which it is encoded, expressed, and stored. We can only think symbolically, that is, through signifiers representing objects, real or not. Relations between signifiers express or represent relations between their corresponding meaning objects. We also model relations among parts of a system as relations among signifiers, meaning or denoting them. All sciences, all types of communications, all systems of belief, all everyday experiences, thoughts, feelings, emotions, and even art experiences are encoded in a certain language. The concept of language taken, of course, in its broadest sense. In order to better understand what and how you are representing through language, you have to understand first what a language is, how it is structured, how it works, what elements, combinations, and possibilities it offers, and also what limits it sets. Continuing from another perspective, the importance of language is also clearly revealed by the advances of cognitive psychology, sociology, and biology. It is known that there are mutual interactions and influences and even causal relationships among the constituents or links of the following circle, which we call the fundamental chain: language, experiences and perceptions, thoughts, reasoning processes, actions, emotions, moods, the body, social interactions, and communication. Any change, action, or stimulus on any of these links causes a wave of interactions and changes in both directions, affecting and changing all the others. This means that every change in every link has an effect on the language link. This in turn means that every phenomenon happening in the other links causes a correlate that is encoded and represented in language. It has, so to say, a translation into language. Linguistic expressions serve as signifiers of states, actions, and changes in the other elements of the chain. Equally important is the other direction. The use of language and time also affects and changes all the other elements. We hope to have shown convincingly why the study of language in logic, linguistics, and psychology should be the point of departure to all other human inquiries. To be able to play the music best possible, you should first try to understand your instrument. We now turn to Unit B, the symbolic identity of the human being. To begin with, imagine reality, whatever that might be, as one big picture or photo you would have in front of you. What acquired language does, expressed in a very simple way, is cutting a jigsaw puzzle into this picture. Language cuts certain pieces out of this picture in a certain way and gives them a certain name, that is, a signifier. It creates meaning objects by separating these from the rest of the picture. In the first instance, you can only talk about these pieces and nothing else. The meanings of linguistic expressions as signifiers are that pieces cut out of the continuum of reality, the pieces as defined by this puzzle. Of course, we have done here a very naive first approximation to language and meanings. Actually, very sophisticated theories exist, but for our purposes, it suffices to give a general idea. Returning to our language puzzle, the first thing to note is that you don't choose the way the puzzle is made. You don't configure it. The forms, the edges, and the contents of these pieces are imposed on you by education, social interactions, etc., that is, society. Most of the meanings are predefined and pre-established, and you're literally forced to accept and use them. So, who are you for yourself and for society? A being defined in and through the pieces of this language puzzle that is a linguistic construction of yourself and of others. What you and society express in language that you are is your symbolic identity. You are a woman or a man, a teacher or an engineer, a husband or a wife, a mother or a father, and so on. But each of these words corresponds to certain pieces of the puzzle, the meanings of which you didn't create. They were predetermined and imposed on you. Do these conventional meanings really describe your experienced identity? If you are a wife or a father or a friend, do you feel correctly described by these conventional meanings? Do you feel that you really are that piece of the puzzle artificially cut out by language? Does your inner self coincide with the contents and borders of these pieces? Or do you experience that these words don't really capture what you are, how you are, who you are? That you are a piece of reality not included in that language puzzle, a piece that perhaps escapes language. Would you need to create a private language, a language of your own, to capture in words your real self? Each of these labels used to describe you contains and implies other labels, and in turn their prefixed meanings. Social roles and behaviors are fixed by them, and so are you. You are a conventionally fixed being. Do you really feel free that way? Do you really feel that this is you? Language, as a social phenomenon it is, can be a jail. The jail is your symbolic, linguistic, social identity. At the same time, language is the only way to escape from it, due to the incredible feature of language of being capable to talk about itself, to change itself. So, learn about language and its powerful structures, think and read about language, analyze language. This will be the only way to free yourself and to break out of the prison of language. The conflicts that arise from this duality of the symbolic self and the experienced self are very complex by their nature, but their comprehension and understanding can be a very powerful tool to restructure yourself. We now begin Unit C, called Basics of Set Theory. As the name says, set theory is about sets, that is, collections of objects. Set theory purports to model certain basic mental operations and capacities. Take a collection of individual objects bearing no relation to each other and being completely arbitrary. The most basic mental operation is the creation of one new object out of them, as the one set that comprises all these individual objects as its elements. The most basic mental operations that set theory tries to mirror are: A. To unify a collection of objects into one new object, the set that contains them as elements. This set is created as a new entity different from its elements. B. To build through diverse operations new sets from given ones, through union, intersection, difference, and complement formation of sets, which we will explain in short. C. To analyze wholes, that is, to decompose them into parts. D. Synthesizing wholes from given constituents. E. Abstraction of common features by defining properties of objects and relations between objects as sets. F. Separating and marking objects out, dividing sets and parts of sets. G. Creating new structures modeled as complex sets containing other sets as elements, and these in turn containing other sets, and so on, without limit to imagination or creativity. H. Finally, the most important fact is that almost all scientific structures can be modeled with the aid of set theory and logical languages. First of all, we may ask what a set is, how it can be defined. If you tried to define a set, you would notice that invariably you would use words like collection, group, etc., which are nothing more than synonyms, which don't define or explain anything. That is why the notion of a set is taken as a primitive, as intuitively given. We must give up trying to define it. This concept is so basic that we must take its meaning for granted. We will give an overview of set theory, which is all we need for our purposes. First of all, in set theory, the existence of certain sets is assumed. Then, some operations to create new sets from old ones are defined, and with their help, axioms are fixed, which are nothing more than rules of construction of new sets out of given ones. This way, a whole edifice of infinitely many and complex sets is built. Almost the whole of mathematics is built from set theory, and almost every mathematical object can be considered a set. It is important to note that every element of a set is itself a set. Sets can contain only other sets as elements. There is no such thing in the standard theory as elements or atomic elements. In the universe of sets, there is only one kind of entity, sets. These can be elements of certain other sets or contain other sets as elements. But there are only sets and a relation between sets, which is called the membership relation, which establishes which sets are elements from which sets and from which not, and nothing more. The next concept we need is that of a subset. A subset of a set is defined as follows. The set B is a subset of the set C definition if every element of B is also an element of C. Example, if C is equal to the set containing 1, 5, Z, X, and 9, then the sets B1 equal to 1 and 9, and the set B2 equal to 5, X, and 9 are subsets of C. A set C can have many subsets. In fact, every set, the elements of which were taken from C, is a subset of C. Now we proceed to explain shortly the main set operations. The first one is the union of two sets. If you have two sets, say L and M, and the new set equal to the union of L and M, is defined as a set containing all elements of L and all elements of M without repeating them. That is, each element of L union M is either an element of L or of M. In this case, for example, if L is equal to AB and M is equal to ADC, then L union M is equal to ABCD. The next operation is that of the intersection of two sets. If you have two sets L and M, then L intersected with M is defined as a new set containing the elements that are common to L and M. That is, each element of L intersected M is an element of L and is an element of M. In this case, for example, if L is equal to AB and M is equal to ADC, then L intersected M would be equal to the set containing only A. The operation of set difference of two sets is defined as follows. L difference M is a set containing all the elements of L that are not elements of M. In our case, if L is equal to A, B, C, D, E, and M is equal to A, B, D, G, and F, then L difference M would be the set consisting of the elements C and E only. In order to define the next operation, which is the complement building of a set, you must have first of all a reference set called the universe. If the set L is a subset of the universe U, then the complement of L relative to the universe U is the set consisting of all the elements of U which are not elements of L. In our case, if U is equal to A, B, C, D and L is equal to C, D, then L complement would be the set A, B. The next important concept from set theory that we need is the concept of an ordered pair. This concept is so universal and important that it deserves special attention. The origin of the creation of this concept was a question about how to create an order between two sets with the sole help of the set operations and concepts defined so far, without having to introduce additional artificial structures. Let A and B be sets. If we build the set C equal to AB, this doesn't suffice to give A and B an order, because C equal to AB is equal to BA. That is, the order of the elements inside a set, here C, is not relevant. We have to figure out another set construction with A and B to impose on them the notion of order. The ordered pair AB, symbolized by the special brackets in red, is defined as follows. It is a set that contains two elements, one of which is in turn the set containing only the set A as an element, and the other one is the set containing exactly the two sets A and B as elements. This definition may seem at first glance somewhat arbitrary and confusing, and in effect it is not the only way an ordered pair can be defined. But this definition has some technical advantages over others, and above all, it implies the holding of the following important property. Two ordered pairs, AB and CD, are equal if and only if A equals C and B equals D. This in turn implies that if A is not equal to B, then AB will not be equal to BA. That is, in the ordered pair AB, it is not the same that A be in the first or second place of the pair. An ordering of A and B has been accomplished herewith. We can conceive of the ordered pair AB as two sets linked by an arrow pointing from A to B to indicate direction in the sense of A coming first and B coming second. We can conceive of it also as a mathematical expression of an arbitrary association between two sets. This association has a direction. That is, we can say that we have assigned the set B to the set A and not vice versa. Now it becomes clear why we have defined previously a sign of a language as an ordered pair, consisting of a signifier object and a meaning object. These two objects are represented here as sets and the association between them as an ordered pair. The huge importance of the concept of the ordered pair lies in the fact that it is a mathematical model of any kind of mental association or linking between two objects that in turn can be modeled as sets. The next important concept is that of a relation, which is simply defined as any set, the elements of which are only ordered pairs. This concept serves as the mathematical tool to represent what we intuitively mean by a relation. For example, the social relation of fatherhood, that is, the relation being the father of, could be mathematically represented by the set of all ordered pairs, in the first place of which is a father, and in the second place of which is one of his children. This sets, which would be a mathematical relation as defined above, would be a model of the real social relation of fatherhood. Of course, fathers and children would be represented here as sets. Now we turn to a special kind of relation which is very much used in science. The definition of a relation allows, for example, the pairs AB and AC both being simultaneously in that relation. Let's take a concrete example to show the necessity of the concept of a function, which we will define as a special kind of relation. Let's imagine that we associated each position of a room with its corresponding temperature. This relation would consist of the ordered pairs being the position in the first place of the pairs and its temperature in the second. To one position, there couldn't exist two or more temperatures. To each position, there would correspond only one temperature. In all applications of science or everyday situations in which you want to assign only one item to another, you are in fact using the special type of relations known as functions. A function is formally defined as a relation in which it does not happen that there are two or more ordered pairs with the same set in the first places and two or more different sets in the second places. That is to say that no two or more arrows could originate at the same set, only exactly one. We have given here two examples. One relation which is not a function, that is R, and one which is a function, that is R1 below. The next definition we need is that of a finite sequence. An initial finite segment of the natural numbers is any set which contains all natural numbers beginning with 0 up to a certain highest number. An example would be the set 0, 1, 2, 3, 4, 5, and 6, or the set containing the first 10,000 natural numbers, including 0. A finite sequence is a function, the ordered pairs of which consist of a natural number taken from an initial segment of natural numbers in the first place and another arbitrary set in the second place. You can see in the slide the example of the sequence f equal to 0a, 1b, 2c, 3d, which is a function from the initial segment I equal to 0, 1, 2, 3 to the set containing a, b, c, d, which is a way to express that the first elements of the ordered pairs are taken from the set I and the second elements from the set M. Why do we need the concept of a sequence? Every expression of a language is built from symbols conceived as sets in our theory, arranged in a certain spatial or temporal order. In written English, for example, the order is spatial. We have to read them from left to right along a given horizontal direction. An English written expression can therefore be modeled as a sequence which, so to say, counts certain symbols from the alphabet from left to right. You see the example of the word learning on your screen. This word can be modeled as a sequence 0L, 1E, 2A, 3R, 4N, 5I, 6N, 7G. In the case of spoken expressions, that is utterances, the order of the sounds is temporal, not spatial, but nevertheless, there is an order that can also be represented as a sequence of sounds, interpreting the numbers as labeling instants of time. Equivalence relations. Now we introduce this important concept because it is a way of modeling mathematically what we conceive, loosely speaking, as similarity in a certain sense, partial identity in a certain way, equality in some sense, or equivalence among objects. To this end, take a set A whatsoever. If you define a relation R, that is a set of ordered pairs in which every ordered pair x, y satisfies that x and y are elements of A, and the following three conditions are met, you call R an equivalence relation on the set A. If a pair xy is an element of R, then x is said to be equivalent to y relative to R. The first condition is, for all x element A, the pair xx has to be an element of R. This condition is called reflexivity. The thought behind this is that every element of A should be self-similar in the intended sense. This is modeled as that all elements of A have to be related to themselves. The second condition is, for every x and every y element of A, if the pair xy is an element of R, then the pair yx is also an element of R. This condition is called symmetry. The idea behind this requirement is that if R is to represent a relation of similarity in a certain way, and x is similar to y, then y should also be similar to x. As the concept of a relation includes that of a direction, with this symmetry condition, both directions are required between the same two elements. Finally, the third condition is, for all x, y, and z element of A, if the two pairs x, y, and y, z are elements of R, then the pair x, z must also be an element of R. This condition is called transitivity. It pretends to model the fact that if a first object is similar to a second object, and this second object is similar to a third object, then the first is also similar to the third. Of course, you have to think about the same sort of similarity in all three cases as intuitive motivation. Now we define the concept of an equivalence class for each element x of A. The equivalence class corresponding to x element A, being the notation x in square brackets, is defined as a set of all y element A such that the pair xy is an element of R. That is, the equivalence class of X is a set consisting of all y elements of A such that the pair xy is an element of R. The equivalence class of X consists, therefore, of all y that are related to it. Now come two important properties of equivalence classes. The first is that if you take two arbitrary elements of A, say x and y, then their corresponding equivalence classes are either disjoint or equal. The second is that the union of all pairwise disjoint equivalence classes is equal to A. The set of disjoint equivalence classes, the union of which is equal to A, is called a partition of A. To prove this, take the classes x in brackets and y in brackets. Let's suppose that they are not disjoint. Then they have at least one element in common, say z. then xz is an element of R and yz is an element of R too. By symmetry, it holds that zy is also an element of R. Take now any arbitrary element of the equivalence class of X, say V. Then by definition, you have that xv is an element of R. By symmetry, it holds that Vx is an element of R too. Because Vx and xz are elements of R, it holds by transitivity that Vz is an element of R. Previously, we had that zy was an element of R. From these last two, it follows by transitivity again that Vy is an element of R. And by symmetry, finally, that Yv is also an element of R. This means, by definition, that V is an element of the equivalence class of Y. As V was chosen arbitrarily, we have proved that X is a subset of Y. We can prove in an analogous way that Y is a subset of X. If both are subsets from each other, then they are equal. So, two equivalence classes are either disjoint or equal. Also easily proven is the other important theorem of equivalence relations. It's not done here. That is that the union of all equivalence classes is equal to the whole set A. As the equivalence classes are either pairwise disjoint or equal, and the union of all of them equals A, one speaks of a partition of the set A by R into these disjoint subsets that are its disjoint equivalence classes. All elements inside a given equivalence class are equivalent to each other in the sense of being related through R to each other. And no element is equivalent to any other of a disjoint equivalence class. Examples of equivalence relations in everyday life. If you take A to be the set of all people, then the following relations would be equivalence relations. X is the same age as Y. X is as tall as Y. X is as heavy as Y. In general, if an attribute or function on A and X being equivalent to Y is defined as having both the same function value, then this is an equivalence relation. That is, if per definitionem xy is an element of R if and only if f of x is equal to f of y, then R is an equivalence relation. Elements that are so related to each other are said to be F-similar.